We learned last lecture that in order to assess the pressure drop or the other relevant parameters for pipe flow that is turbulent, we needed to use the friction factor. And the friction factor is defined as 8 times the average wall shear stress divided by rho times the average velocity squared in the pipe or in the channel. To analyze this in terms of flow, we want to now consider a pipe section. So this pipe section has a length of L. This is a circular pipe as drawn. And in order for this to be steady flow, which is what we've been studying in fully developed flow, the steady flow, the forces must balance. And there are only two forces acting on the fluid here. There's the pressure force and there's the wall shear stress exerted by the wall on the fluid. So the pressure forces are simple. It's just the area of the inlet times the pressure at the inlet minus the area at the outlet times the pressure at the outlet. And then the force exerted by the wall on the fluid is 2 pi r naught, that is the circumference of the pipe, times L. So that gives you an area of the internal wetted surface of the pipe. That whole internal wetted surface area times the average shear stress along the wall. So these two magnitudes have to be the same in order for the fluid not to be either accelerating or decelerating in this section of pipe. So we can rewrite this. The areas are the same at the inlet and the outlet for a circular, steady, cross-sectional area pipe. So we're going to just call that A. And we're going to say that so the pressure forces are just A delta P. And so we have A delta P is 2 pi R naught L times that average shear stress. Delta P, of course, that means is defined as P in minus P out. We know the area. The area is pi R naught squared. The area of a circle times delta P is equal to 2 pi R naught times L, and again, that average shear stress on the wall. The pi's, of course, are going to cancel each other. One of these r's is going to cancel, that r there. So we have a relationship for the pressure drop as a function of shear stress. So we have 2L over R naught times that average wall shear stress. So that's an engineering result. If you know the wall shear stress, you can calculate the pressure drop. If you know the pressure drop, you can calculate the wall shear stress. That assumes that there is no significant height change. So I'm going to put a note here. That assumes that delta Z is equal to 0. There is no height change in the pipe. We will add a height change later. If we need one, we can use it. But we're going to study pipes that aren't going up or down. So this is a useful relationship for pipes that are not making significant height changes. But that's not actually what we want. What we want is to relate all of that to the friction factor, not to the wall shear stress, because we don't know the wall shear stress. So let's go ahead and see if we can do that. So the friction factor, the definition of the friction factor is F is equal to, as we said above, tau average over rho U average squared. And so we want to replace this with this using the friction factor. So I'm going to solve this equation for tau W, for that wall shear stress. So I have the wall shear stress in terms of the friction factor. So if I do that, tau W average is equal to, here it is, I'm going to push that rho U squared over to the other side. That multiplies F, and then I'm going to divide by 8. So that's my wall shear stress in terms of the friction factor. And now I can plug that into this equation up here to get my pressure drop in terms of the friction factor. So I have my pressure drop is equal to 2L over R naught, and then times this stuff, rho U squared F over 8. All right, so that looks pretty good. I'm going to obviously divide there and get a 1 over 4. So delta P equals 2, I don't have 2 anymore, sorry, L over R naught times rho U squared average F over 4. But I also don't want to leave R. This is related to, this relationship is almost always done in terms of D instead of in terms of R. So I'm going to replace that. So I have L, and this is D over 2, times rho U squared F over 4. And so there's my D, and then of course 1/2 times 1/4 is 2. So my final relationship for pressure drop in a pipe in terms of the friction factor is L over D, rho average velocity squared over 2 times F. Usually it's written like this: delta P equals F, friction factor out in front, L over D, U squared average over 2 times rho. So that is the pressure drop for a pipe in terms of the friction factor, and that's all if delta Z is equal to 0. If delta Z is not equal to 0, we can add the delta C component to the left-hand side. So we'll add rho GZ over here. So that's going to be an additional force caused by gravity, and we can say that that will equal to the same thing. So over 2 times rho. So that's an additional source of essentially pressure difference here, where we have, this should be delta Z. So I'll write it again. Delta P plus rho G delta Z is equal to F L over D U average squared over 2 rho, and this is squared. And that is delta Z is equal to Z in minus Z out, and delta P is equal to P in minus P out. So either way, if you have no delta Z, you just have this relationship here. And if you have to have a delta Z, a significant delta Z, you need to add that into the left-hand side to account for that effect, and over this side. Either way, 2 good engineering results if you know the friction factor. So now we have to figure out how to calculate that friction factor.